Today on How It's Made. Inflatable watercraft. It's sink or swim. Couscous. The non-Italian pasta. Modeling dough. Creativity takes shape. And wicker products. The upside of being a basket case. Today's inflatable watercraft range from rafts and dinghies to canoes and kayaks. They're less expensive than conventional boats and easier to store and transport. You don't need a trailer, just throw your boat in the trunk. Then unfold and inflate it when you get to your aquatic destination. Whether it's a raft shooting the rapids or a motorized boat gliding across a calm lake, an inflatable watercraft begins with sturdy, waterproof material. This company uses a millimeter-thick PVC fabric that has a nylon or polyester fiber core. After workers trace and cut out the pieces that will form the boat, they connect them with a strip of the same material, fusing them together using a machine with a propane flame. The intense heat melts the surface of the PVC until the pieces bond. Here's that bonding action in slow motion. Next, they fuse a strip of pure PVC to the underside of the joint. This ensures that air won't leak out of the boat where the pieces connect. Inflating the boat will pull on the material surrounding the air valve, so they reinforce that area with a round piece of PVC called a doubler. This high-frequency welding machine applies 127 kilograms of pressure and heat-generating FM waves to fuse the doubler in place. Then they cut a hole in the middle of the doubler for the air valve. Next come the cones. Cones support the weight of the motor and enable the boat to plane, to rise above the water when traveling at high speed. Using the propane flame machine, workers seal together the ends of the boat, then insert the inside cone piece just before they close her up completely. They finish off the seal using the high-frequency welding machine, then pull the cone piece through. They inflate the boat until the pressure forces the cone piece into place. They seal all around it with heavy-duty caulking. Stick on the outside cone piece, then screw it securely in place. They inflate the boat fully now to perfect the seal and to expel the excess caulking. Now they install what's called the transom, a plank of wood that supports the motor at the rear of the boat. They cover it in boat fabric using a plastic resin-based glue that's resistant to the fiery heat of the sun. They apply the same glue to the piece of material that will become the underside of the boat, then position it in place. After gluing on a bumper made of hard PVC, they coat the boat's underside in a liquid plastic resin. This protects the bottom when the boat runs aground over rocks and sand. They test inflate the keel, a stabilizer that runs the length of the boat. Then they deflate it and begin installing the floor. The floor is made up of 5 connected pieces, 3 made of aluminum and 2 made of fiberglass, plastic, or wood. The hole in the floor is for the keel's air valve. After inflating the boat, they inflate the keel. Now they can take measurements to determine where to position the oars. First, they glue on the oar locks, the pieces that hold the oars in place. The oars are made of aluminum, so they're lightweight and they won't rust. The motor is 6 horsepower to 50 horsepower, depending on the size of the boat. Couscous is a traditional staple of North African cuisine. It looks like a grain, but it's actually pasta. These days, few people make couscous from scratch. Even in North Africa, they usually buy their couscous ready-made and just steam cook it. Couscous is the product of culinary simplicity. It's made from one ingredient and one ingredient alone: wheat. Most often, the durum species of wheat. When you remove the grains, grind them, and sift out the finer flour, you're left with a coarser wheat flour called semolina. That's the flour from which they make couscous. The first step is known as hydration. An automated food processor measures about 1/3 water to 2/3 semolina, then mixes them for 3 minutes. The flour particles absorb the liquid and bloat into a raw dough. The dough particles then go into a rotating drum, where they spin for 7 minutes. This rounds them into balls of varying sizes. A screen inside the drum sifts out the big clumps. The raw dough balls go into a giant steam cooker for 15 minutes. The intense heat, 100 degrees Celsius, cooks the dough by gelatinizing the starch in the wheat. As the couscous balls exit the steam cooker stuck together, giant revolving blades break them up. The soggy couscous now enters a rotating dryer where it spins for 18 minutes. This removes 22% of the water. The remaining moisture is necessary to prevent the couscous from drying out in the package. As the couscous pours out of the dryer onto the conveyor belt that funnels it to the next station, you can see that the balls are much drier and relatively uniform in size. But they're still steaming hot, so they go off to a refrigeration chamber for 2 minutes to cool. As the couscous exits the chamber, it runs through a screening machine that separates the balls, called grains, by size. Medium and fine couscous go off to their respective storage silos, while grains that are too big or too small go back to be reprocessed. The couscous making process, from wheat semolina to the finished product, has taken just 45 minutes. As we've seen, most of the cooking's been done by the factory, so all the consumer will have to do is steam this ready-made couscous for just 5 minutes on the stove or in the microwave. This factory packages its couscous in bulk quantities as well as in smaller meal-sized portions. Today, ready-made couscous comes in many different flavors. And depending on the dish you're making or your personal preference, you can choose medium grain or fine grain. Plain Plain or flavored couscous is becoming an increasingly popular side dish, an alternative to rice, potatoes, or noodles. You can even buy main course couscous kits that come with a can of vegetables and a packet of sauce. There's nothing little kids love more than digging their hands into a mound of squishy modeling dough, then rolling and shaping it. It's a hands-on experience in creativity, made all the more fun by modeling doughs that come in bright colors and yummy scents. Just in case little Billy decides to snack on his artistic creation, this scented modeling dough is made entirely of food ingredients, flavorings and colorings, salt, flour, hot water, and some secret ingredients the company won't divulge. The key to achieving just the right consistency is meticulous measurement. They use electronic scales to precision weigh each ingredient. Bit by bit, they pour the dry ingredients and flavorings into the mixer. The amount of hot water they add varies according to the color and scent they're producing. The proportions are about 30% water to 70% dry ingredients. The last ingredient is food coloring, in this case, cherry red. For the modeling dough to come out just right, the mixing time has to be precisely 3 minutes and 20 seconds. When the dough comes out, it's roughly the consistency of pie dough. It's quite hot from all that churning, 70 degrees Celsius to be exact, but there's no need to cool it before packaging. It goes right into a machine called the stuffer, which cuts it into container-sized portions. The finished product is soft and malleable enough for endless hours of play. Besides smelling delightful, this modeling dough doesn't crumble, doesn't stick to things, and won't stain clothes or upholstery. A machine called the container distributor lines up the plastic containers. Then the stuffer drops a wad of hot dough into each one. As the containers move down the line, on goes a cover stamped with the production date. A compression roller then runs over the cover to create an airtight seal. Last but not least, a colorful sticker to boldly identify the scent. The containers pass through a metal detector, a precautionary measure in case some metal shards wore off the machinery and landed unnoticed in the dough. The company lab is continually developing new scents. This brand comes in 36 different scents so far, from a variety of fruits to kid-friendly foods. The lab is also constantly experimenting with new colors, though some, such as purples, are quite difficult to produce. Children, of course, can make their own colors simply by combining existing ones. If you leave the modeling dough out of the sealed container for too long, it'll dry out. But because this brand is water-based, not oil-based like some others, you can revive it. All you have to do is add a few drops of water, knead it a bit, then put it back in the sealed container. After a few hours, your scented modeling dough will be as good as new. Wicker is thin branches or vines flexible enough to be woven. Many plants can be used for wicker, such as willow and rattan. Quality wicker is very durable. You can find antique wicker furniture that's as sturdy today as in its heyday. The oldest piece of wicker on record dates back to 1400 BC. Archaeologists discovered it in Egypt, where in ancient times people used wicker chairs. Hand-woven wicker furniture was the rage in Europe and North America in the 1800s. To meet this demand, trade schools churned out master wicker weavers. But by the 1930s, manufacturers developed a paper fiber to mimic the look of wicker and large mechanized looms to do the weaving. Today's genuine wicker items are usually made of rattan core, rattan palm tree branches stripped of their bark, then processed into different diameters and profiles. At this workshop, they use a manual loom to weave wicker hampers. Taking what's known as flat oval rattan core, flat on one side, rounded on the other, they run horizontal strands through vertical strands in an under and over pattern, working between the hamper's wooden frame and its fiberboard lining. They keep the vertical strands taut by tying them to weighted ropes. It's important to keep moistening the rattan with hot water to keep it supple enough to manipulate. They weave one thin round strand after every 13-centimeter high section of flat oval. There's no structural reason for this pattern, it's purely aesthetic. A wicker wastebasket begins with a base that dictates the shape. They insert vertical stakes of round rattan core along its perimeter. Then below the base, bend each stake over the next, then under the one after that. This forms what's called the foot border, a bottom rim that holds the base securely in place. Now they insert a wooden form and begin weaving. First, a small section of round rows, then a large section of flat oval ones. Slowly and patiently they work their way to the top, never resorting to glue or staples to hold the strands together. Only a hook to compress the rows for a neat and tight weave. Every so often they use pliers to tear off a stray fiber. Now for the finishing touch. They braid what's left of the vertical stakes into a decorative top rim. This particular braiding technique is very complex, requiring all 10 fingers and a special tool to pry stubborn strands apart. They snip off the excess with a cutter. When they're finished, they remove the modular wooden form. Its components are numbered so they'll know how to reassemble them for the next basket. Another more decorative way to finish the top of a basket is this arch technique. They trim each vertical stake, bend it into an arch, then tuck it into the basket 3 stakes over. This measuring tool ensures the arches are of equal height, while this metal device creates a space into which to tuck each stake. Wicker weavers create magnificent designs by combining various shapes and sizes of rattan. A strand can be as thick as a pencil or as thin as a needle. While this doesn't quite fall under the category of wicker, it's not uncommon to see wicker workshops use other natural materials. Here they're weaving a chair seat out of cord made from seagrass. There's also wicker seating material. This pre-woven sheet is called cane seating or rattan peel. It's made from the bark stripped off the rattan branch. First, they force it into a groove in the chair's wooden frame. Then they glue in what's called spline, a strip of rattan core with a pointed edge. They wedge that edge into the groove, hammering it down to hold the rattan peel in place. Then they trim off the excess. Because wicker is wood, it can be stained or painted, or left its natural color. Whatever the finish, they give it 2 or 3 coats of varnish for protection. Today on How It's Made. Electric baseboard heaters. Nothing but the warm, hard facts. Molded pulp containers. This ain't pulp fiction. Prepared chicken. Passing the buck. And video games. Warning, this report contains graphic scenes. Electric baseboard heaters are inexpensive, easy to install, and practically maintenance-free. Unlike radiators, they're inconspicuous, and they take up very little space. And best of all, you can control the temperature room by room. A baseboard heater is simply wires and a heating element in a steel casing. They make the element using a strip of paper-thin aluminum 19 centimeters wide. It's lubricated with soap, then goes through a forming machine. A die punches the strip into little squares called fins. They measure 16 by 20 millimeters each and have a circle in the middle. The machine pierces the circles and cuts the fins apart. This machine churns out 600 fins per minute. It stacks them on steel tubes, the lengths of which vary according to the length of the heater. As each tube fills to capacity, a worker takes it away to be wired up. Elsewhere in the factory, meanwhile, they make the heater's casing, using what's known as cold-rolled steel, a flexible type of steel that can be worked without using heat. After a squirt of oil for lubrication, the first die cuts holes for attaching the baseboard to the wall. Then the second die cuts holes for attaching the heating element to the casing. Now the steel travels through what's called the roll former, a machine whose series of rollers successively bend the flat strip of metal, one fold at a time, into the shape of the casing. From start to finish, 20 rollers make 20 bends. The process takes exactly 146 seconds per casing. After the last fold, a computer-controlled die cuts the casing to the required length. The higher the heater's wattage, the longer the casing has to be. Models range from 300 watts, about half a meter long, to 2,500 watts, almost 2.5 meters long. Next, they put a steel junction box on each end of the casing. These hold the wires that the electrician connects to the house wiring. Workers spot weld both junction boxes simultaneously. After a thorough washing, computer-controlled sprayers coat the casings in paint powder. Then it's into an oven for about 20 minutes at 185 degrees Celsius. This transforms the powder to liquid, drying it instantly. After running a red wire for the electrical current the length of the casing, they rig up what's called a linear high-limit temperature control, a safety device that prevents the unit from overheating and catching fire. Gas inside the temperature control expands under intense heat, triggering the device to cut the current. Now they install supports to hold the heating element in place. They're made of satin coat steel, a rust-resistant metal. As the element heats up, it naturally expands. To prevent it from scratching against the metal casing and making annoying noises, they install a heat-resistant plastic bushing. Now they connect the red wire that'll carry the electrical current to the heating element's black wire, capping it with a wire connector. They clip it to the cover of the junction box, easy access for the electrician installing the baseboard. Then they close the junction box cover. At the other end, they connect the red wire and the black wire to the temperature control wire. This runs the electrical current through the safety device at all times. After a voltage test, they close her up and snap on a panel to cover the element. Being toasty warm is now just an installation away. Molded pulp isn't exactly a household word, but it is a household item. Chances are you've got an egg carton in your fridge that's made of it. This thick cardboard-like material can be shaped into a variety of containers, such as those drink carriers they give you at the fast food restaurants. Farms ship out their eggs in trays called filler flats. These flats begin as recycled paper. Old phone books, newspapers, magazines, cardboard, pretty well any product made of paper fibers. The factory even recycles its own flats that have been rejected by quality control. The raw materials go into what's called the pulper, a giant blender that mashes everything up and blends it with hot water that's 43 to 65 degrees Celsius. The hot water swells the fibers, causing them to break apart. After 20 minutes, they become pulp, a watery mixture roughly the consistency of hot oatmeal. The pulp exits out the bottom of the pulper through a filter that screens out plastics and other contaminants. Shaping the flats is a fully automated process. Formation molds descend into a vat filled with pulp. A vacuum sucks the mushy mixture onto them. Water jets rinse off the excess. Rotating above are transfer molds. They grab the flats off the formation molds and move them onto a conveyor. Before the transfer molds grab the flats, though, a brush applies a water-based lubricant. This ensures the flats won't stick to the molds. It's just like greasing a baking pan. The molds themselves are made of bronze, plastic, or aluminum, depending on how long the factory intends to use them. They're covered with a stainless steel mesh. This mesh ensures an even vacuum through the mold so that the pulp spreads over it evenly. The soggy flats now go into an oven for 12 minutes to dry out. The 205 degrees Celsius heat evaporates the water. This bonds the fibers together, forming a rigid material. After they exit the oven, a device appropriately called an upender flips them up so that they stack into each other. A built-in counting mechanism triggers the machine to section off the required number of flats per package, then compress them, and seal them in plastic film to keep the dust out. The factory uses the identical molding process to make 4-cup drink carriers. These too go into an oven to dry out the pulp, but only for 6 minutes, half the time the filler flats need, because this product is smaller and lighter. Automated compactors stack the finished drink carriers. Then workers compress them for packing and shipping. The factory also makes disposable urinal bottles for hospitals. They add chemicals to the pulp to make the bottles liquid tight. These molds are three-dimensional and lined with mesh on the inside. When they submerge into the pulp vat, a vacuum sucks in the pulp. When they resurface, water jets rinse the excess pulp off the bottlenecks, and the vacuum sucks out the water. A spiked conveyor belt transports the bottles to the drying oven. They dry at a lower temperature than the flats and drink carriers do, 176 degrees Celsius, and for a longer time, a half hour. This ensures the chemicals making the bottles liquid tight cure thoroughly. While urinal bottles can't be recycled for sanitary reasons, drink holders and filler flats are recyclable, making them extremely environmentally friendly. In the year 2001, Canadians ate 31 kilograms of chicken per person. Given that rate of consumption, if we had to process the poultry ourselves, chances are we'd be in a rather foul mood by dinner. Thank goodness for chicken processing plants. The chickens arrive at the factory with their feet, legs, and heads already cut off. What's left are the breasts and wings. The slaughterhouse also removed the internal organs. A conveyor belt transports the chickens to the cutting and deboning zone, a bustling assembly line operation. Workers prop each chicken on a cone-shaped stand in order to have both hands free to work on it. Cutting up a chicken properly isn't as easy as you might think. The workers get special training. It's crucial they keep their knives well sharpened and wipe them after every 5 or so chickens. The first cuts remove the wings, starting on one side and positioning the knife horizontally in line with the top of the cone. The worker makes an incision where the wing joins the shoulder, then cuts downward across the back of the chicken. Then a quick cut and twist to detach the wing. It's the same procedure on the other wing. The incisions at the wing-shoulder joint must slice through the tendon completely. Otherwise, detaching the wing is difficult. And struggling with a slippery wing while holding a knife in your hand can result in serious injury. The next cuts remove the skin and breasts. They peel off the skin, then pull on the 2 breasts and make a quick incision to release them. They slice the breasts apart, carefully checking for bones that might have broken off from the carcass and be hiding in the meat. The next cuts remove the tenders, the meat located under the breasts. Workers make an incision in the middle, just under the wishbone, and down the length of the carcass. This detaches the tenders, enabling the next worker on the line to pull them off. Meanwhile, waiting in the wings are the wings. Workers load them onto a machine appropriately called the wing cutter, a mini Ferris wheel that takes the wings for a little ride, right into a sharp knife that chops them into 3 sections: the drumette, the chubby part with the most meat, the winglet, the middle part, and the wing tip, the pointy part with barely any meat. This factory transforms the meatier drumettes and winglets into frozen, ready-to-eat chicken wings. The first step in that process is seasoning. Workers load the pieces into a giant drum. As the drum rotates, they inject the seasoning, barbecue or honey garlic, for instance. After about an hour, the chicken wings come out evenly coated. Now these freshly seasoned wings go into a gas-fired oven where they bake at approximately 250 degrees Celsius for 8 to 11 minutes. They come out fully cooked and ready to eat. They go into a freezing mechanism for about a half hour, then to the automated packaging department where they're sealed in a bag. These chicken pieces, wings, tenders, and breasts, are prepared differently. After seasoning, they travel through a rotating drum that coats them in a flour and breadcrumb mixture, then into a second drum for a second coat. Next stop, a 40-second deep fry in canola oil, just long enough to adhere the coating. Then from the frying pan into the fire, as they say. Well, into the oven, actually. After 20 minutes at about 250 degrees Celsius, these chicken pieces are fully cooked and ready to be frozen and packaged. They started out a generation ago as simple black and white ping pong games on a TV screen. Today's video games are vivid, sophisticated, and fast-moving, driven by state-of-the-art computer software featuring the latest in high-tech graphics. It all started in 1952 with a Cambridge University PhD thesis on human-computer interaction. The student invented a primitive tic-tac-toe game on a vacuum tube computer, the very first computer game with graphics. A team at MIT designed the first recognized computer game in 1962. Then, in 1972, a Stanford student invented the arcade game Pong, which later became a home video game to play on your TV set. It all begins with the people who form what's called the core team. They brainstorm in meeting after meeting to hammer out the concept, how the game will look, how it'll work. Then they plan out the production schedule, assigning who'll do what, when. They break down the game on paper and color code the components. Then they post them on a bulletin board that'll act as the production's nerve center. Now work on the artistic concept begins. Artists sketch out the characters and backgrounds on paper in a scene-by-scene storyboard. Meanwhile, graphic artists recreate those storyboard drawings three-dimensionally on the computer. This step enables the development team to use the latest in computer animation technology to bring the game elements to life by adding colors, textures, shading, and, of course, movement. After developing a preliminary version of each character, the animators superimpose a skeleton. By manipulating the skeleton, they make the character move. They experiment with different movements until they decide on which ones they'll use for the game. The animators have to design every movement each character can potentially make in the game. That's 700 movements for this main character alone. Once that's done, they flesh out the character's features and costumes to completion. The evolution of the characters from the first pencil drawing to the final version is quite remarkable. Other animators work on the backgrounds, the game's playing field. Once they have a rough version laid out, they refine it by adding details, colors, and textures. To give it depth and dimension, they use virtual lighting to create shading and shadows. To advance the storyline, this particular video game is interspersed with 1-minute animated movies. These segments, called cinematics, are animated in high resolution to produce a top-quality image. The interactive game, on the other hand, is in low resolution, because computers can't process high-res images quickly enough for fast-moving play. So the animators have to create every character twice in both high and low resolution. Meanwhile, for the cinematics, they animate the storyboard using rough draft characters. This is simply to calculate the timing and to map out a clear path across the backgrounds, so that the characters don't collide with the scenery. To make the cinematics action look realistic, they use a technique called motion capture. The animators videotape themselves performing the action, then use animation software to reproduce it on the computer. Computer programmers create the video game's menu settings, among other features. Computer engineers design the artificial intelligence, the brain that runs the game. It's made up of thousands of computer codes. For the cinematics, actors record the characters' lines in a sound studio. An audio technician mixes the voices with music and sound effects and synchronizes everything with the action. Now they take the video game out for a test drive. Do the characters move the way they're supposed to? Do they go where they're supposed to? Or do they run into trees and walk through walls? This is the development team's last chance to rid the game of any bugs. After that, the company can finally market this video game and hope it becomes a hit. Today on How It's Made. Prepared mustard, putting on quite a spread. Violins. We had to pull some strings to show you this one. Nuts and bolts, forging ahead at high speed. And toilet paper. Roll 'em. We eat it on hot dogs and hamburgers, on sausages and sandwiches. No condiment cuts the mustard quite like mustard. The ancient Romans took the mustard seed to what is now France, and by the 9th century, big-time mustard production was underway. Yellow mustard and Dijon mustard have a few ingredients in common, but that's where the similarity ends. Not only are they prepared quite differently, they're derived from different varieties of mustard seed. Yellow mustard is made from the seeds of the white mustard plant. Turmeric and paprika provide the yellow color and sharp flavor. The other ingredients are salt, water, and white vinegar. The powdered ingredients go down a shaft to a mixing tank containing the water and vinegar. Yellow mustard's proportions are roughly 60% water, 20% vinegar, 15% seeds, and 5% salt and spices. The last ingredient to go in is the mustard seed, hull, bran, and all. The tank's rotating mixer blends the ingredients for about an hour at seed-crushing speeds reaching 265 kilometers per hour. The tank's contents empty into several stainless steel mills. Inside each one, a pair of synthetic stones grinds the seeds, a process known as stone milling. That grinding action heats the mixture to about 60 degrees Celsius. The liquid thickens into creamy, bright yellow mustard. Before bottling, they perform what's called a finesse test. This ensures the mustard is smooth enough. If its particles are more than 1/4 of a millimeter big, the factory adjusts the milling stones closer together to produce a finer grind. They make Dijon mustard from brown mustard seeds, sometimes mixed with other varieties. And they usually use 2 types of vinegar, cider and white. The ingredients ferment in the tank for 12 hours before mixing. That's what gives Dijon mustard its strong flavor. After mixing, it's the same stone milling process we saw before. Here's what the inside of those mills looks like. A rotating stone rubbing seeds against a stationary stone. The same principle as an old-fashioned mortar and pestle. Dijon is made with twice as many seeds as yellow mustard and 20% less water, which is why it comes out thicker and denser and needs the occasional stir. Filters screen out any particles larger than 1/4 millimeter. The factory saves these coarse pieces to put into specialty mustards. Now the creamy smooth Dijon mustard goes into a stainless steel tank. A slow-speed revolving mixer removes the air, which would otherwise turn it brown and dull its flavor. The yellow mustard tanks also have mixers to remove air and to keep the condiment well blended. Both Dijon and yellow mustard have to cool overnight before bottling. From start to finish, it takes about 20 hours to produce yellow mustard, about 32 hours for Dijon, the extra time due to the fermentation period. Yellow mustard has a 15-month shelf life, while Dijon stays fresh for a year. Both should be refrigerated after opening to preserve their flavor. Mustard is a condiment that even health-conscious eaters can enjoy. It packs a lot of flavor in just a few calories. It contains just a small amount of fat, somewhat more if the manufacturer uses oil in the recipe, but it's still a cholesterol-free food. The violin developed in the 1500s. Evolving from a series of guitar-like instruments that musicians played with a bow. While the violin is best known for classical music and gypsy music, today you hear it in pop, country, bluegrass, and even jazz. First, they cut a piece of maple, then split it in half to expose the grain in mirror image. They melt down glue flakes made from animal hide, then bond the pieces together. Violin makers use only glue, never nails or screws. These pieces of wood will form the back of the violin. After 4 hours, the glue is dry and they can remove the clamps. Using a small plane, they even out the surface. Then they trace the violin's shape and cut it out. They shave the surface, sculpting a downward slope from the middle using an even smaller plane. Then they carve a groove along the circumference. After dabbing it with glue, they insert what's known as purfling, a reinforcement made from a thin strip of hardwood, usually maple. Finally, they carve the reverse side to the right form and thickness. Next, they make the sides of the violin, known as the ribs. First, they soak thin strips of maple or sycamore and press them against a heated bending iron to curve them. Then they glue the strips around a form, connecting them at the top and bottom and at the corners with small blocks of wood. They clamp everything together and let the glue dry for 4 hours. Next, they glue thin strips of wood, called counter ribs, onto the edge of the ribs. This enlarges the surface so that it's easier to glue the ribs in the back together. They make the violin's front, or belly, from a solid piece of spruce. To the underside, they glue a spruce support bar called the bass bar. Sound escapes through the 2 curved slots called F-holes. They cut out and carve the violin's neck and scrolled head from a piece of maple. Then they glue it to the body. They sculpt the fingerboard from ebony, a hard wood that's durable enough to withstand centuries of violinists' fingering. Using a tool called a peg hole reamer, they make holes for the ebony or rosewood pegs around which the strings are wound. They coat the wood with 4 or 5 coats of varnish, depending on the color, then polish it with several coats of oil over several days until the finish is shiny and silky smooth. Next, they insert the sound post. This little pine cylinder conducts sound and supports the belly against bowing pressure, so it's critical to position it in precisely the right spot between the belly and the back. It's not glued, but rather wedged into place. The bridge isn't glued either. It's held in place by the pressure of the 4 strings, which they feed through the ebony tailpiece and wind onto the pegs. The bridge has little notches in which the strings sit. The violin is finished. They make the bow from horsehair and a high-quality Brazilian wood called Pernambuco. They bind the hairs at one end with a strong sewing thread, then burn them and seal them with wax to prevent fraying. This end goes into the frog, the wooden box at the bottom or heel of the bow. They cover the frog with a mother-of-pearl lining, then slip on a ring made of nickel, silver, or gold to prevent the hairs from tangling. Next comes the screw that controls the tension of the hairs. They comb the hairs to make them parallel, then insert them into the tip of the bow, known as the head. They tighten the screw until the hairs are taut. Finally, they rub on rosin, a sticky pine tree resin that keeps the bow from slipping off the strings. At How It's Made, we pride ourselves in showing you the nuts and bolts of how everyday items are made. So it's about time we visited a real nuts and bolts operation. We sure couldn't do without these tiny but essential pieces of hardware. If only they weren't so darn easy to lose. Nuts and bolts are made from what's called steel wire rod. After spending up to 30 hours in a furnace to soften it enough to be worked, the wire rod goes into a bath of sulfuric acid to remove any rust particles. It's rinsed in water, then coated with phosphate, a chemical compound. This prevents the steel from rusting before the bolt forming begins and lubricates the steel to make forming easier. They form the bolts by cold forging, shaping the steel at room temperature by forcing it through various dies at high pressure. The forming machine first straightens the wire rod, then cuts it into pieces slightly longer than the bolt length. The extra will become the bolt head. Each piece goes through a die that makes it perfectly round, then through a series of dies that progressively shape the head of the bolt on one end. The machine heads up to 300 bolts per minute. Here is what the heading stages look like in slow motion. This die creates a slight collar. The next one turns it into a round head. Then the last die transforms that into a hexagonal head, the most common shape. Next, the machine forms the opposite end of the bolt. A tool called the pointer shapes the bottom of each bolt, creating what's called the chamfer, the part the nut catches onto. Here's the bolt before and after the chamfer. The bolt needs threads to enable the nut to screw onto it. Once again, they use the cold forging method. High-pressure rollers press in the thread pattern, as we see here in slow motion. This is the actual speed, up to 300 bolts per minute. During each production run, they take several samples to verify dimensions. They use various measuring devices, a micrometer to check the bolt's length, calipers to measure the width of the head, and a ring gauge to check the threads. To make the nuts, they use a process called hot forging. They cut steel bars into small pieces known as slugs, then heat them to 1200 degrees Celsius to make them malleable. As we see here in slow motion, hydraulic hammers punch the slugs into hexagons, while a die pierces the hole. Then a tool called a tapper drives into the hole to cut the threads. That black liquid is a lubricant oil to minimize the wear and tear on the tappers. The nuts and bolts now go into an oven at 870 degrees Celsius for about an hour. This gives them the required strength. Then a rapid cooling in oil for 5 minutes solidifies the steel's internal structure. By now, the steel is hard but brittle, so they heat the nuts and bolts for another hour. This removes their brittleness, yet maintains their strength. The quality control team pulls samples off the line, measuring how much force it takes to break them. If a bolt meets its minimum strength requirement, it passes inspection, provided the break occurred in the threading, the weakest part. Finally, packaging, labeled among other things by size and grade. Toilet paper is probably the most indispensable item in your home. After all, it's not something you want to run out of at the wrong time. Most of us probably take our rolls of toilet paper for granted. So you may be surprised to learn that bathroom tissue, as it's properly called, is a relatively new invention. The Vikings used wool. The ancient Romans employed sponges, and French royalty wiped with lace. Then in 1857, an American entrepreneur figured that people had had enough of using leaves and corn cobs and newspapers and mail-order catalogs. So he invented therapeutic paper, as he so tastefully named it. Toilet paper came only in piles of pre-cut sheets until 1890. That's when one company introduced bathroom tissue on a roll. Ever wonder where all that recycled paper goes? Well, look no further than your own bathroom. Many brands of toilet paper begin as recycled paper. The bales of paper drop down into the pulper, a giant tank with an agitator similar to what you see in a washing machine. It mixes the paper in lukewarm water for about 10 minutes, transforming it into what's known as pulp and screening out all the bits of metal and plastic. Now they have to take out the ink. The ink removal system injects the pulp with air. The ink particles attach to the air bubbles, which rise to the top. The system then skims off the foam, leaving the pulp ink-free. Next, the pulp passes through a series of rollers which squeeze out the water. This dries out the soggy pulp, enabling it to absorb the chemicals they'll use to bleach it. Revolving knives now chop it up again to prepare it for the bleaching process, the details of which are a closely guarded trade secret. The bleach turns the gray pulp a pure white. The company says it does this without using chlorine or other toxic chemicals. They spread the wet pulp onto a flat screen that runs through a hot dryer. In less than a second, the pulp dries into a delicate paper a mere 1/10 of a millimeter thick. Each spool holds 75 kilometers of paper. That spool now feeds a machine with rollers that emboss a pattern, in this case, a waffle print. The pattern isn't just aesthetic, It also makes the paper thicker and therefore more absorbent. Elsewhere in the factory, production is rolling, so to speak, with 2 strips of cardboard, each 8 centimeters wide. The machine coats the underside of the top strip with glue, then winds the 2 strips diagonally together to create a continuous cardboard tube. The machine then cuts the tube into 165 centimeter lengths. The tubes ride an elevator to the toilet paper zone. There, 2 giant spools of paper feed what's called the winding machine. The 2 sheets come together to form a 2-ply toilet paper. The paper then winds onto a cardboard tube, creating a super wide roll of toilet paper. When the roll is full, a blade automatically cuts the paper and winding resumes on the next tube. The machine automatically seals the end of the roll with glue to prevent unraveling. A circular saw slices the super-wide toilet paper roll into 16 standard rolls, each 10.2 centimeters wide. The toilet paper is finished and ready for packaging. This batch is for commercial use. Each roll is individually wrapped in paper. Check out this slow-motion wrapping action. Toilet paper destined for residential use gets wrapped in transparent plastic, 4 to 30 rolls per package.